Hello and Assalamu alaikum. My name is Usman Hassan, and I'll be presenting you my ML2 project, which will be based on predicting market response using machine learning algorithms in contrast with MCMC algorithms. So let's start. So we'll start off by importing these libraries, which will be used for our task ahead. So this template is being imported from Machine Learning 1, where I made a template which included several functions, including functions related to machine learning algorithms and predictions. This chi-square test will be used later on, which will be used to find dependency of categorical columns with the target column. So moving ahead, this is the preview of our data set. And as we can see that there are 2,240 rows and 29 columns. So there are not many rows to work with, but we have a lot of columns where we can work our way around and see which features will be helping us predict the target column very accurately. So each row corresponds to a customer who have either responded or accepted the campaign offer or not. And this moves us to the main goal, which of this project, which is to identify those customers who are more likely to accept the offer and who are more likely to accept the product or service offered by the company. So this will help us target. This will help target relevant customers and maximize the campaign profit or the company profit. So this is the detail of the features. As we can see, most of them are integers already, except for a few, rightfully so. And then moving ahead, we have to remove the ID column because it doesn't make sense to keep the ID column. And DT underscore customer is the date when customer got enrolled with the company. So we converted it to date time just in case. And let's start the ETA and deal with the missing values. We can see that the data is mostly filled and there are only 24 missing values in the income column. So we're going to deal with these columns. And this is the count of the categorical. So the categorical column has unique values. So the count of those unique values. So just to see if there are no incorrect values or no null values in the column. And doing so, we found that the values of 1900, 1899, and 1893 doesn't seem reasonable for birth year. So we have to change this. This seems like an incorrect value. So first of all, these values will be converted to null. And then after converting it to null, we are going to replace it with the mode of the year birth. That's the easiest way to fill this, the year birth column. And once it's done, so this is the ANOVA test of income with education because the income column has the missing values. We have to see where we can fill those missing values with. So income and education is highly correlated. The p-value, as we can see, is insignificantly small. And this means we can accept our alternate hypothesis and say that these two are dependent on each other. So so for example, a PhD level education has this much salary income, and graduation level has this much salary on average. Same goes for masters and 2-1 cycle. And then wherever we find the missing values related to PhD, we fill it in with the average of that. And same goes for graduation, master, and 2-1. So as we can see now, there are no more missing values. And moving ahead, we can now do the numerical analysis of our income. It's probably not normal, which makes sense because the income value is high when there are a lot of PhD candidates. So over here, the income value makes sense. It doesn't seem like an outlier. It may look like an outlier, but it can be easily justified as a genuine case. So we're going to leave it as it is. And then these are the graph of categorical column. This is the target column, by the way. So we can see that there's a huge imbalance between the classes. So people who did not respond are far too many than people who did. And same categorical count of other categorical columns as well. And we go ahead, as you can see, the complaints. This is the complaint column. So there are very, very few, very insignificantly small number of people who made a complaint. So I think this table is not going to be very useful for us. So if we perform chi-square test on response in education, we can see that it is dependent. Response is dependent on the education because the p-value is insignificantly small. And if we do it on complaint, we can see that it's independent. So complaint will not be used to predict the response. So if we go ahead, move forward. So over here, what I did was I extracted the year from GT underscore customer just to see if our target column is actually influenced by just the year of the customer enrollment and just the month of the customer enrollment. And it finds out that they are actually dependent. Both of them individually are dependent. So it's better to use the date itself. So we're going to remove these two columns again and form a correlation heat map to see which columns. It gives you a perfect visualization of which columns are mostly affected by the target. Now, if we move ahead, DT underscore customer is converted to string format because now we are moving towards the encoding part because machine learning cannot be done without encoding. So DT underscore customer is converted to string. All the 7 characters are converted to string. And now we are going to encode it. So DT underscore customer is done through label encoding. And marital status is done through label encoding. There are only a few categorical columns. And I figured out that the education is of a hierarchical nature. So based on the ordinal encoding technique, I gave 0 to basic education and 4 to PhD education. It forms a scale. So it's like ordinal encoding. So once we have encoded, this is the encoded data set. All of them are numerical. And convert everything to integer or float. And now we can move towards the machine learning part. The first step is to find the error rate. This is done by using k-neighbors algorithm. And for several number of k values, I found the error rate. And I found out that the k value of just above 5, it could be 6 or 7, the error rate comes minimum. And this error is, by the way, the mean squared error. So if we move down and we use the k value of 6 and do the machine learning algorithm of k neighbors, these are the predictions. We found that the accuracy, this is the accuracy and F1 score. It seems reasonable, but we'll move ahead. K is equal to 7 gives this accuracy. It's slightly changed, but let's try other machine learning algorithms. So if we apply other machine learning algorithms, using the data set, we see that logistic regression is providing a good F1 score because accuracy is not the only thing that we see. We have to see the F1 score as well. Both of the classes should be predicted correctly. So the best one yet is logistic regression and gradient boosting as well. And now we are going to oversample and we're going to try logistic regression with varying thresholds. We're going to tune the parameters of the logistic regression algorithm. And once we do that, over here, I used predict underscore proba instead of the traditional predict underscore in traditional predict because I'm going to change the threshold of the 1 and 0 mark. Because by default, if the value is, the probability is greater than 0.5, it will give the class 1, and if less than 0.5, it will give it 0. So these are all the probabilities of the predictions. And over here, I'm using the ROC AUC curve to predict the threshold. And once I do this, I can see that AUC score is all right. It's really good. And these are the geometric mean. And I have to find the maximum geometric mean index because that's where the accuracy will be the best. And that's where that threshold I need to take. So this is the maximum geometric mean at index 24, and at index 24, the threshold is 0.24. So if I apply a threshold of 0.2, just to be in case, and see the accuracy, it doesn't change much. Still an accuracy of 72 and F1 score of 47 through logistic regression. So recall is the best. So this is the problem with ROC AUC. It improves the recall, but it compromises other accuracies as well. So recall is the best as threshold 0.2, 82% recall. but other performance metrics are still compromised. So in order to get the optimal threshold, if we are looking for recall as the only performance metric, ROC AUC curve is the best one. So now we're going to see the relevant features alone. We're not going to see all the columns. And this is the importance, the feature importance of all the columns. And you can see the recency and income are the most important features, followed by date the customer joined and other relevant columns as well. So let's try this out with a combination of different trees and different thresholds. So when different trees and different thresholds were calculated, then the machine learning was done for these relevant features. It turns out that logistic regression is still the best one so far. And gradient boosting has been really amazing as well, 82% accuracy and 53% F1 score, and a good recall as well. So gradient boosting has really worked good with random forest feature selection. So so now that we have done feature selection, now we'll do dimensionality reduction techniques, and it includes LDA and PCA. So the problem with LDA is that we have two classes only. So if we have two classes, the number of features that we can get is only one. So we're going to compress the features into one feature only to predict the two classes. And LDA, one thing also is good about LDA is that it takes into account the class distribution. So we apply the linear discriminant analysis model and fit it and then transform it. We have this linear discriminant as the only column. And this becomes our new data frame. And when we apply machine learning on this, we get the following results on all the algorithms. And we can see that logistic regression has performed well on this as well. The recall is good, the F1 score is good. And now if we perform PCA with 5 principal components and 10 principal components, 2 methods were tried. And PCA has deteriorated the results very badly. And the reason for this is because it is a supervised learning case, and PCA is more suitable for unsupervised learning because it doesn't take into account the class distribution, and it basically focuses on compressing the variance as a whole without taking into account class distribution. So in contrast, LDA has provided much better results. So this was the machine learning part. And if we move towards the MCMC, I did MCMC on Google Colab instead of Jupyter Notebook because it was taking too long for the chains to converge. So this is the Google Colab file. So all the initial steps have been done, imported the relevant libraries, PyMC3 and RViz, because we're going to use this to converge the chains and form a model. And this is the encoded data frame that I put into my drive. And this is the preview of the data set. All of them are encoded. And this is the function of random forest feature selection that we're going to use, because in MCMC, we're only going to use a few features only. So we have to make sure that those features are really important and are really influential. So if I do the random forest feature selection, we can see that recency and income still tops the list. Yeah, with 8 trees. This is with 8 trees. So recency and income are still on top of the list with higher feature importance. So moving along, this is where we actually create our target and predictors. So response from the data frame becomes our target. And for the initial step, I'm only checking the income as the only predicting value. And over here, I have normalized it manually by taking the mean. It works similarly as a standard scaling or min-max scaling. Train test split usually done. I've taken a test size of 0.35 because a test size of 0.2 was not enough of a test size to see the results, because the test size was too small. So I took a test size of 0.35. Here we are making the model. So basically, over here, xc underscore train becomes our x data, and y underscore 0 underscore train becomes our y data. Alpha and beta are the parameters which are going to be used for the prior function. And over here, this is the likelihood function. Yeah. And this is basically, this means that we are going to sample 1,000 samples, 1,000 data points from the posterior distribution itself. So this is telling the PyMC3 to use MCMC to sample from the target distribution, which is the posterior distribution. And this is the, you can say, the likelihood function, because we don't know the parameters yet. So this becomes a likelihood function. And once these 1,000 samples are being generated, first few will be burnout because of the warm-up phase, where prior and likelihood will be used to sample the data points from the posterior. And posterior then incorporates our prior for unknown parameters, but then updates them regularly after observations of different data points. So over here, we can see these are the parameters, the estimated parameters, which is considered, I don't want to say optimal, but considered to be the parameters that are going to be used for the test case. We can change this value, the sampling value. Higher the number of values, more accurate the results will be. So let's move along. So this is basically, so this is just a way of checking if the MCMC algorithm has worked fine. This lets us check that MCMC algorithm didn't suffer from any MCMC pitfalls or any other problems that are encountered in MCMC. So once that's done, we plot the posterior. This actually means the same thing that is being described over here. It's just a summary. And if we move along, we can see that data has been captured quite normally, quite perfectly. We have plotted the predictive, prior predictive and posterior predictive, and plotted the whole thing, the observed and the predictive value as well. And by using this, we are going to test it on our testing set. This becomes our testing set, and we are going to sample the posterior predictive of this model, trace 0, and call it YPRED. So this is YPRED. It forms an array. Just like in the neural network case, we get multiple results for one value, and we just choose the one, or we take the mean of this. So these are several arrays, each corresponds to one output. So if we take the mean, we get these predictions, and they're all probabilities which come from sigmoid. Sigmoid function is described over here. So this is sigmoid. We're using sigmoid to calculate the probabilities of our deterministic function, the parameter theta. And if we move along, these are our probabilities. And now we have used the default value of 0.5, because that's what all the machine learning algorithms do. They use the default value of 0.5, and anything above 0.5 will be 1, and anything below will be 0. And the results were not very accurate, because we can see over here only 780 values out of 784 test size, only 780 were predicted as 0 and 4 were predicted as 1. And these 4 were also wrongly predicted. So they're not correct values. And we can see this over here because the precision recall and F1 score is 0. However, the accuracy is 86% because all of these are zeros. So if we try ROC AUC curve that we did in machine learning part and change the threshold somehow, this didn't help us either as well, because the precision recall is still 0. Okay, so we are going to try something else. We are going to add another feature in the MCMC for better model learning. Instead of income, over here we use the Metropolis Hastings. So this is the Metropolis Hastings algorithm. And we'll see if Metropolis, by the way, the model above is NUTS algorithm by default. So over here, I have changed it to Metropolis Hastings and see if it affected the results in any way. So again, the parameters, estimated parameters, posterior, and this is our test case. And predictions, we can see a lot of ones. And now we can see the predictions by taking the mean. And now if we check, we can see 395, it's almost half, which also is very alarming, because the number of ones in our training set are very less. The classes are highly imbalanced. But anyway, it did improve the accuracy, and the well, the accuracy is compromised, but it did improve the F1 score and recall. I mean, it's better than 0. So Let's try something else now. We check the threshold values as well, and the threshold doesn't help us either. It's still very similar to 0.5 as threshold. And now we have included another feature. The reason why we did a random forest is because we can see the influential features, and income and recency were on the top of the list. So we are going to use another feature, recency. And recency is, by the way, the number of days since customer bought or accepted the last offer. So this has a huge impact on the response. Again, test size as 0.35. We use Theano library because it allows us to share the number of features together and club them together. Instead of, if we had used one feature, we wouldn't have required this Theano feature. So formula has slightly changed. The boundary decision becomes a little. The formula becomes a little different. We're still using the same parameters, alpha and beta, for the prior, and we're using Nuts algorithm. And there are the estimated parameters again. And this is the posterior distribution. And if we test it on the predictions of our test data, we are just repeating everything with using different models. And if we see the accuracy over here, the recall has improved significantly, but accuracy is still 26%. It has decreased. So let's keep trying on different things. RSC AUC has not been our friend in the MCMC case as yet. So one thing in MCMC that we didn't take into account was the highly unbalanced classes. Obviously, the people who didn't respond were far too many, and we were using sigmoid function to find the theta values, and logistic regression can struggle sometimes with unbalanced classes. So, and also decision boundary is affected by theta as well. So when classes are unbalanced and the boundary will tend more towards the class which has more probability, more accuracy. Okay. So instead of sigmoid, we are going to use softmax function. I read that in my blog that softmax function is supposed to help with the imbalance of classes in the MCMC. So instead of sigmoid to calculate the theta value, we are going to use softmax. So again, the same model. We are using the same train test plate scenario, same library Theano, and then over here, all we did was add softmax instead of sigmoid and run the same thing all over again. These are the estimated parameters. This shows that it has worked fine. The posterior looks a bit abnormal, unusual. And if we test it on our testing set, this forms our predictions. This is the probabilities, which doesn't make any sense. So maybe the softmax function didn't prove its worth either. So let's see what the accuracy is like. Let's see the numbers. And the accuracy, you can see that only 5 ones were predicted. So we can't expect too much. We can't expect a better F1 score. Maybe the accuracy has improved, but the F1 score you can see is still 0. All these 5 values were predicted wrongly. So the softmax function has failed. But let's try to balance the classes like we do in machine learning by oversampling it. So we have few number of ones. So we're going to increase the number of rows which has ones by duplicating it. And let's do this. So yeah, so over here we applied random oversampler and put it on X and Y being our predictors and our response target, X being our predictors. So the shape makes sense. And we apply the same thing again using the Nuts algorithm. This time we have used the Metropolis Hastings. And we can see that 2 chains, so the MCMC had run 2 chains for me, each starting from a different value and converging at the same point. So this depends on the computer RAM as well. It finds it on its own. So these are estimated parameters. traces, plotting the posterior, everything all over again. And then these are the predictions. These are the predictions probabilities. And if we apply the threshold of 0.5, it predicts 980 as 1, which is also very alarming. So the accuracy has decreased, but the recall and F1 score still comes out to be much better. So maybe oversampling has improved the score quite significantly. So yeah, oversampling has improved the score quite significantly. And over here, we can conclude that MCMC still requires a lot of working. The computational memory and the computational strength was definitely a limitation in this project. But as far as machine learning is concerned, logistic regression and gradient boosting has worked flawlessly well. But there are more work to be done on MCMC, and if it's done rightly, so MCMC can produce just as good results as the machine learning algorithm. Thanks so much for listening.